Okay, so welcome everyone for this first roundtable. So the goal of these roundtables are just to have a rather informal discussion about topics that are in a sense common to all the lectures that we have heard so far, and also to have some kind of prospective questions. So as you saw on Slack, we have prepared a few questions for the panelists here, but we will likely not have time to go through all of them. And the idea also is that you will have the possibility to interact, to either give your own opinion on some of the questions, or also to ask some questions yourself. So you can comment on Slack, but the best is that you take the mic and you speak up. So we are going to start. So first roundtable, so we have Pierre Le Saffre, Nathalie Izard, Vianney Le Bouteiller, and Benjamin Godard, that you all know because they just spoke. And we are going to start with the first series of questions. So the first series are really questions about models of interstellar media. And the first one concerns really the center of this summer school, which is the comparison of the Milky Way and external galaxies. And so the first question that we would like you guys to discuss is that how can we apply models of the galactic ISM to other galaxies? And eventually, what are the limitations of this approach? We can start with that. So does anyone want to start? I have a random. No. I have a random generator if you want.
Well, okay, my answer to students is always a dust grain is a dust grain wherever it is, So when I am asked to do models for CISM, okay, they're applicable to protoplanetary disk with some adaptations. So that's, I think you can apply it when you are aware of what is inside. It's always a question of the black box, which you have to know what is behind. And of course, you will have to adapt the elements you put in, depending on the metallicity and everything. But a silicate is a silicate and an hydrocarbon is an hydrocarbon. So at least for dust, I think at some point.
Someone else? I mean, after you have different types of silicates. I mean, that's
Yes, but first you have the size, and then you have the details. But I mean, a solid will be heated the same way if it's heated by the same mechanisms.
Okay.
Could the composition change and be very different? And maybe the size could be processed much more violently and maybe be much smaller. I don't know. So, but you think we have the tools to?
Yes.
Okay.
The tools are always the same. That's what I mean. Yes.
Oh, sorry. So regarding the mistake I made on my lecture concerning the injection problem of turbulence, so there is in fact no problem for our Milky Way, but there is one for other galaxies, and which people are now trying to address by adding some artificial driving in their simulations. So I haven't tried to apply these very rough physical ideas that I taught you to other galaxies, but maybe it's worth trying and checking what's the ratio of the various injection mechanisms in other galaxies. But similar to what you said, I think the tools we may have in hand, but it's just a matter of scaling them and trying to apply them to very different environments.
Oh, okay.
So my question is more or less related to what Nathalie was saying, where now recently at the higher redshift, we are now seeing the weird distributions where the dust, for example, is not perfectly aligned with the stellar distribution and the gas distribution. And the Milky Way models don't necessarily work that clearly anymore. Of course, there's still the lack of data at higher redshift. So are there potential methodologies that any of you could think of that could then work to help understand what's happening at higher redshift using the things that we are certain of that work from the Milky Way?
Yeah, there is also the shift between C2 and O3, for instance, that is observed with ALMA, and that's very difficult to model because if you didn't have the spatial resolution, you would think it's a single object and you try to do the same models as usual, and you wouldn't even think of it. But because there's this spatial offset, you have to think of it, and you have to think what is the object you're trying to model, really? And for me, that's the way I think of it. Like for this question, it's about the ISM, but if we're trying to think of it as the object we're trying to model, I work on dwarf galaxies. They are not spiral galaxies. So some dynamical effects are going to be different. There will be minor interactions and mergers with spiral galaxies that won't happen with dwarfs. The interactions with the CGM is going to be very different. There will be galactic fountains and super winds that will develop in the flattish galaxies, things like that. And when you're trying to model the galaxy as an object like that, with all its complexity, then it's completely different. You cannot just assume a Milky Way model, of course, right? But if we're talking about the ISM static conditions, then the microphysics are the same as long as you change the parameters. And so there's the dust, the abundance patterns will be different for different galaxies. The metallicity would be different. And as a result, the dust to gas mass ratio will be different. So these are all prescriptions that we should change compared to the Milky Way ISM. And anyway, I deviated, but that was my answer to that question. And for your question, how I would approach that, I have no idea. I think the best is to try to think of the configuration that we're seeing. Are we seeing a single object? Are we seeing two different components of galaxies? Like for instance, there will be, there are DLAs, Dampleman alpha systems, and sub-DLAs, and these are in interactions. And especially at high redshift, I would start thinking that maybe there are some galaxies that haven't formed stars yet. It's a very dense environment between, with a lot of systems, a lot of proto-galaxies with different shapes, different masses. And it will take some time for some of them to start shining really. And so maybe it's not a single object. That would be my first thought. And if you were thinking of a single object to model the C2 and O3 and find that spatial offset, I think you would have a very, very hard time. And I wonder if it's the right approach to think of a single object actually. But that's just my opinion.
As a follow-up, if we're taking precise examples, for instance, the model in the galaxy are made for metallicity of 1. So do you have benchmark sources for other metallicities that can anchor the model? Because as long as the models does not have comparisons with observations, you never know whether you have the right answer.
So for benchmarks, the typical benchmark will be the Magellanic Clouds, because in some cases, in some wavelength ranges, some tracers, you can start resolving maybe not a single PDR, but what's close to a single PDR front. And then that can serve as a benchmark. And there is a program, a JWST program by it's Karen Sundström, is she here? No. The goal is to focus on a single PDR in the SMC, if I'm not mistaken. So, and the goal is to calibrate PDR models at a 5th solar metallicity and to anchor the models, as you say. That will be to 1/5 solar metallicity, though, and I insist on that because things start to break down below 1/8, 1/10 solar metallicity, and this is really where we need to calibrate the models. What was that? How do we know? But because the abundance of pHs starts to decrease very sharply below 1/10. The lack of CO detection, it happens below 1/8 solar metallicity or so. There seems to be something that changes dramatically below 1/10. I don't know what it is exactly. Maybe Fred, you have some ideas on that, but yeah. But anyway, so the SMC is only 1/5 solar metallicity, which is good, but.
Yeah, so it's all a question of trying to account for the systematic variation between the Milky Way and other systems. So metallicity seems to be a really crucial parameters, but it might not be the only one. you might want to look in the parameter space. I mean, because at a given metallicity, you have different star formation histories, and that can have led to different enrichment histories, not only at the element in dust, and also in the phase mixing in the galaxy, which is very important for the material universe. So I guess that's
yeah, and maybe metallicity is too rough a term, and we should consider relative abundance, C over O, N over O,
abundance
which
patterns.
can be very different according to the star formation history.
Yeah, what change also when you change the metallicity? Oh, well, there are many things that change when you go to other galaxies. There is the injection mechanisms. What change also with metallicity is the very nature of the distribution of the gas in its multi-phase environments, because you change a lot of physical processes like the thermodynamic, the thermal instability. So you will change the very probability distribution function of the distribution of your different phases. And this is, you are talking about benchmark. I'm not sure that we are at for this part. I'm not sure that we are at the stage where we have benchmarks. There have been a lot of models that have been developed in order to see how the distribution of gas change when you change the metallicity, for instance, or when you change the injection processes. But are we sure that these models, I mean, are we sure of the results of these models based from comparison with observation? I'm not sure at all.
Also, something which changes, so I have two remarks. We may be lucky that the Milky Way looks a bit like an isolated systems, but at higher redshifts, there are way more mergers, and this is very hard to account for. Also, CGM raining on the galaxy may change a lot of things, and this has not been studied very extensively. And the other remark, I lost it. Yes, we think we understand the Milky Way, but already when we look at our first neighbor, SMC and LMC, we don't understand anything. So I think this should humble us.
So, I mean, so we have already started to answer the follow-up questions to that, which is, I'm putting them back on the screen. So you see, oops, we went too far. So yeah, so how peculiar is the ISM, the Milky Way? So we already started to discuss a bit about that. And what are the ISM invariants? So Natalie already started to say that. I mean, a silicate is a silicate, whoever. But it's a different look at this question about the systematic differences between the Milky Way and other galaxies. Is that so? Pierre, you say the fact that the Milky Way is an isolated system. Are there other peculiarities of the Milky Way that would question? So, except for what we discussed, the metallicity, the isolation, the fact that it's going to be, I mean, different from other galaxies.
Well, I guess the radiation field.
I didn't get what are you saying?
The
Sorry.
difference, what are the main difference? The radiation field, of course.
The radiation field between the Milky Way and the galaxies. Yeah, well, I guess, well, I'm not an expert of extra galaxy or other galaxies than the Milky Way, but yes, you change the radiation field. Also, you change the density of photons, right?
Mm-hmm.
If you are looking at a starburst
And the shape.
The starburst galaxies, then well, whatever you are going to observe out of the starburst galaxy will be mostly the reprocessing of UV photons. You will see less, in fact, the reprocessing of the other source of energies of these galaxies. This is my because the density of UV photon is much larger. It's as if you have thousands of Orion region in a very small region, in fact.
Maybe I can add something about the radiation field and the energetic sources at low metallicity, because it's something I started to think about not that long ago. It's the fact that compact objects at low metallicity are going to be different. For instance, you're going to have a direct collapse black hole at low metallicity that's going to lead to more massive black holes. And that's because of the opacity of the stellar atmospheres at low metallicity. You're going to be left with a much larger mass at the end. That makes a more massive black hole, more luminous. And so these are things that are seen observationally, that are also expected theoretically. And it's something that is not yet ingested in all the models and the simulations. But it's like the dust to gas mass ratio. At some point, you have to assume that the dust to gas mass ratio is not linear with metallicity, and it's not the Milky Way value, even less. And so the compact objects need to have some kind of prescription that depends on the environment, in this case, the metallicity. So that's one thing. And then, so it concerns any type of actually high mass X-ray binaries as well. There is a known larger number of high mass X-ray binaries at low metallicity, and each high mass X-ray binary is more luminous at low luminosity. So if you start thinking about XDRs, for instance, in a very low metallicity environment, that might start becoming interesting. Even if you don't have an AGN in your source, in your galaxy, you might have a collection of high mass X-ray binaries. It's something that the full Athena would have been great to do. The new Athena will be, I guess, not so good to do it, but to distinguish the ultra-luminous X-ray sources in nearby galaxies, it will still do, I hope, pretty well to do that. And it will give us a new knowledge really on the importance of the off-nucleus X-ray sources in nearby galaxies. And these off-nucleus X-ray sources in extremely metal poor galaxies are very different than those you can find in the Milky Way, the so-called micro-quasars.
And they have an impact on the heating of the gas and everything.
Right, exactly. So the impact of that is well, it's basically an XDR. So they will partially ionize the neutral gas, heat it, and so the temperature is going to be warmer, the electron fraction is going to be higher, so it's going to change the chemistry, and it can change a bunch of things. And even on large scales, you could think it might actually regulate star formation if you exaggerate a little bit.
And what about the cosmic rays?
Well, I don't know about the cosmic rays in other galaxies, you mean? Well, I don't, honestly, I'm not competent to answer this question because I know our own galaxy. I don't know what differences there can be for when you go to other galaxies. So are there studies in MIT2 that show that you have a much higher cosmic ray rate and things like that?
In our presentation, I gave some references. So like I said yesterday, the range that we've seen of the ionization rate in nearby galaxies is about the same range as in the Milky Way, meaning that you get for the average value in the disk of the Milky Way, you see that also in the disks of nearby galaxies. It's about the same value, 10 to the minus 16 or 10 to the minus 16 per second. But if you look at the galactic center of the Milky Way, it's like 3 orders of magnitude higher. And apparently it's the same thing also that is observed in the nuclei of nearby starburst galaxies. But in general, it correlates with the star formation. So people tend to take a prescription that depends on the star formation rate and these kind of things. But it mostly depends on the star formation right now in the prescriptions, in the models that people are using, and not so much the metallicity. And as far as metallicity dependence is concerned, I have no idea. I'm not even sure I'm aware of one reference that tackles the topic. If somebody knows it, I'm actually interested.
So we are insisting a lot about differences, but I think we should insist also on what is common, because else there is, what is the current way, ESM invariants, there must be some in order to be able to make sense of the extra galactic. So I understand that it's other questions.
No, the invariant is that everything varies everywhere. I mean, you don't have to go to another galaxy to state your models. No. If you look at the JWST data for Perseid and Orion, there are 2 PDRs. And believe me, if you take the dust I don't know the gas. If you take the dust you put for the Orion bar, you have no chance to be able to explain the dust you see in the ourselves. Because the dust to gas mass ratios are not the same, because the hydrogen to carbon fraction in the grains are not the same. And you also have to change the proportion of silicate to carbon you have to put. So voilà, I think at some point.
So you could still make a model where you try to predict the evolution of the different phases of the ISM as a function of metallicity, for example, because here you are talking about the fact that you have variations within the Milky Way, because you have variation between phases of the ISM. But you also have different phases in external galaxies, so you could try to predict what are the dust properties in the diffuse ISM of the SMC, in molecular clouds. I mean, you could have the same process.
But some people have tried to do that already, like Jérémy Chastenay, and probably Lucy knows a lot about that. But it's, I mean, people have been trying to do that, and they have been using different models to be able to find convergences between models, not to find model-dependent results. But I don't know that very well, to be honest. So.
I'm not sure this work can be done with all dust model that exist. And I'm thinking especially with the new model from Drain and Hensley, can you fine tune it like you can do with the other models that, for example, are plugged into the stem?
But they would have to fit their dielectric function each time they are finding OSCD. So it would be a new model each time.
So it's less convenient to do that.
I mean, a normal user in this room cannot do it, and I cannot do it, for instance. It's impossible. They only can do it.
Yeah, and their old model, you could do that because you could vary the relative composition, the relative abundance of carbon versus silicate-based dust. So it's just to say that this new model has very strong hypothesis, and you can use it to compare your favorite object to the diffuse ISM, and that's it. You will not be able to fine tune and understand what are the differences, in fact, in terms of dust composition, if you want to study dust physics, really.
Which is not the case of the Tevis model, which is physically parameterized.
So I don't know many outer galaxies, but it seems to me that an invariant is the number of phases, very hot, warm, neutral, medium, CNM, the presence of dust, stars, a gravitational island, sometimes spirals.
So does the S curve of the ISM still apply when you drastically reduce the metallicity, when you change the heating rate, the cooling function and everything?
I think that yes, it does. I'm not sure over which range it will apply, but there have been recent work done by Shmuel, for instance, where he has tried to change the metallicity and see what happens to this S curve. I think that it stayed there over the study. I don't remember the range of parameters they explore during their work. So.
So are there questions or comments in the room? Maybe we can go to the next question. So I'm going to share again to show you. So now it's a question, a matter of point of view. So could it be possible that the way we are modeling the interstellar media, so it means all interstellar media, is limited because it's an in-post problem biased by the observation that we are getting. So meaning that we have a particular viewpoint given by the tracers that we get from the interstellar media, but it's a very convoluted way to look at its physics, and we have to in a sense, diagonalize the system when we model it, and it might not be the best way to look at it. So do you have any idea about that?
Probably biased, I would say.
Yeah, well, biased, of course. I mean,
Yeah, for me, it's surely strongly biased, but I think you were saying that yesterday. I mean, you model what you can see. What you cannot see, you don't model. So this is a problem.
sometimes
Oh, yeah,
it's
okay.
very-
But there is also a problem of the range of wavelengths that is accessible to us, right? There are a range of wavelengths of photons that we won't be able to see. And there is this range of the soft X-rays. We can. Well, if there are some events in the interstellar medium that produce this kind of photon, and if there are important events, we won't be able to see them, so we won't want to model this stuff. Sorry?
I'm saying you won't see the soft X-rays directly, but you can see the consequence of the soft X-rays, which will be to hit some gas. And so you will see increased cooling from some lines, and you can try to guess whether it's due to the soft X-rays. That's difficult.
Yeah, well, this will be like in H2 region where you have these soft X-rays are absorbed and reprocessed to something else. Well, yeah, but if you have some process which somehow produce this kind of thing, which are not the regions that we know, and if they are reprocessed by more diffuse matter, let's say a little bit everywhere, then this is something that we don't see, and this is something that we won't model. So this is just one example. I have some strongly biased.
Yeah, it's related to what I said yesterday also, but and I'll be a bit provocative, but in the way of thinking of a model for a full galaxy, I became convinced that it's wrong actually to just adapt the model to the tracers that you have. So if you have 1, 2 tracers, you will tend to use a simpler model because you think you have very few constraints, and that it's better to do a simple model than no model at all, or than a complex model that is completely over-determined or whatever. And in some cases, actually, it works. And some assumptions, so there is a lot of literature on the topic with very simple models for external galaxies, but they were concentrating on parameters for which this kind of assumptions of using a simple model, single component, is okay. And I think they did a good job. So I won't argue that they were wrong there. But if you start tackling more complex parameters, like the ones I described yesterday, the escape fraction, the mass of molecular hydrogen, the tracers of molecular hydrogen, then a simple model just can't capture that. And you're going to get a biased answer for sure. And so I think it's, so I would argue that it's better to use a realistic model, even if you have very few tracers. And sure, if you use deterministic approaches, then you have many more parameters than tracers, and you won't be able to say anything. If you have probabilistic approach, you're going to have some kind of probability. And this probability is very useful. It's your result. Basically, it says that with the information you have in hand, you have a given percentage chance that your parameters falls within that range, and that's it. And if you want to improve that, then the only way is to use priors that will be motivated by some simulations, or you can also simulate your own data and try to see whether if you use a single component, you get the same answer as multiple components. That's what I tried to show yesterday. But these tests are very useful to know if the parameters you're considering depends or not on the model representation that you have in mind. And then, of course, there is the hierarchical approach. If you use Bayesian statistics, that's one way also to gain information from other pixels in a map or other objects within a sample. And for the galaxies for which you have very few tracers, then you're going to increase the knowledge from the other pixels or other galaxies in your sample. And that's one way to improve the situation with a complex model and a few tracers.
Yeah, maybe I want to ask a question to you in the room. If you, during your work,
I may have one remark. We may have a few tracers, but we may have a lot of galaxies. If you have a large sample of galaxies, statistics, you can say something.
so the question was, during your work, have you encountered something which you would have got completely wrong by using the picture we have of the Milky Way nowadays? Or maybe a new discovery of a process which was completely absent in our Milky Way. And, maybe it's fine. Or...
In fact, I have the reverse questions. Why are you working so hard to make those models if they are useless elsewhere?
Because it's fun.
You know, once I got a referee who told me you are doing useless complexity. And 1 year later, we used this complexity to analyze observations. And I knew it was a referee, and I sent him an email. Ha ha ha. Because you know, it's not
What was his name?
No, but you know, it's never useless to do good physics or good chemistry. It will always useful at some point. At least you understand really what you're doing. I mean, it's oversimplicity is never a good thing.
But that's very important to state again that the physical and the chemistry laws almost certainly are the same through the universe. Okay.
Yeah, and it's never.
It's not useless.
Yeah, and it's never useless to be physically or chemically correct.
So the next question is, for me, is how to improve the model in the galaxy, or to improve the modelings we are doing in the galaxy in the way we can use them in other conditions in extragalactic. So what do you have to do to go to do this step?
Well, you have to make everything public. I mean, the tools. First. So that's, you have for instance, when you deliver a model, a dust model, if the tool to calculate the temperature of the brain is not public, people cannot adapt that to their environments. So I think that's the first step. And make something very comprehensive for the user, because otherwise it's so complicated at some point, nobody can understand. So on our side, so we have the codes to calculate everything are public. And we make the optical properties public. And we made a website where we explain all the basics of the model in a very simple, in a way which is more simple than what is in the paper, of course. And I think that's the first step. But then
I have two things I wanted to add. First, regarding your previous question about the utility of the model, this is one way to look at science. Is we should do something that is useful. But another way, this is the sense of your question. Well, is it worth to do something that is not useful? Pierre likes to cite Cyrano a lot of time. It's more beautiful when it is useless. And the point is that I think when we are developing model, it's not to necessarily apply them to other environments. We don't care. The goal is personal enrichment. It's an egoistic approach where we are trying to know more and more personally. Huh? And even if we find again something that has been found by many people before, who cares? Huh? It's not a problem. You are trying to. It's a personal growth research. Okay, so this is the first point. And then regarding what we need to be developed in models to apply them to other galaxies, this was the second point. I don't have the answer. The only part of answer that I have is everything is driven by observation. You have an observational problem. This is what will drive what you need to include in your models, right? So if I don't know, Pierre was asking, oh, did you find something that, I don't know, underline some very strong question about our view in the Milky Way? Well, this is what we need to look for. We need to look for some evidence that will drive the development of models.
So I agree with what you just said. And I wanted to add that you don't necessarily have to look for something very different, but just talk to each other. Like this kind of event is very nice because you're coming from very different horizons. You have your own problems. And sometimes when you just try to describe your problem to somebody else who has a very different point of view, you will get the solution.
There's one thing I'd like to add is that we're talking about the galactic ISM versus extragalactic ISM, and the Milky Way ISM is more diverse than maybe what we think or what we usually work on when we work on the Milky Way ISM. If you go to very large galactocentric radii, the metallicity is going to be significantly lower, actually, and there is an abundance gradient that is not flat. It's a little bit lower, and maybe that's already good enough to see whether the PDR models are working fine there. I don't know if it's easy to find the PDR there, but and then the environment around compact objects, for instance, there are microquasars. So of course, the ISM is less transparent than in the metallicity environments, but still, it's very interesting to see how the radiation field impacts the ISM around such sources and to calibrate our models on that. And we're talking about Milky Way ISM, not extragalactic ISM. So they can be exotic objects and moderately metal poor gas clouds in the Milky Way itself. And maybe we should try more to expand a bit the environment within the Milky Way to bridge the gap with at least the Large Magellanic Cloud, for instance. Observationally, it's very difficult. That's one problem, yes.
Yeah, because so to come back to this question about the fact that it could be a ill-posed problem, you know, that we can be looking at the thing the wrong way. We have been talking a lot about the observable, how to account for them, but there is also probably the way we parameterize our model. For example, Pierre showed that if you want to study turbulence, looking at the power spectrum, it's a very good way to understand it. And for example, if for some reason nobody knew what a power spectrum was, could we understand turbulence the same way, or would it be more difficult?
I would say the power spectrum is a bad way to look at turbulence. Yeah, I mean, there is much more. I think we know very little on turbulence. It's the game of, I mean, it's the same story of we are looking for our keys where under the light, the street light. But there's
I have a doubt, which like observationally it's very tough to understand, and theoretically it's much tougher. The point is the ISM is very complex, and on small scales it's much complex. And in external galaxies, the structure is gonna be different. Let's say different type of galaxies, its structure is going to be different on small scales, and the density is going to be different. Diagnostics are going to be different for outer regions, inner regions. The point for me, which is not understandable, is when we are taking different diagnostics on different zones in this, let's say I work on H2 regions, so I can give a better example for that. So we take different diagnostics on outer skirts, in inner regions, in mid regions. Similarly, if we'll go to extragalactic H2 regions, they have different structures and different densities. How should we look into it? Like, I don't understand if you're taking oxygen to density, nitrogen to density, or sulfur to, it's different for different values. How we gonna take an average one? How we'll think about it? The structure is completely different for different bodies in different, like extragalactic, our Milky Way. So how we really think about it?
So your question is related to say a single H2 region in an extragalactic, I mean, in an external galaxy, or the collection
I'll be okay with the comparison too. Like, how should we think about it? There are different diagnostics in different reasons. So on average, what shall we think it like?
But you're talking on average because you have different regions within a galaxy. not between galaxies or
No, yes, inside a galaxy.
Inside a
Yes,
galaxy, yeah.
yes.
I would preach for my approach, which is just to consider that you have a collection of regions, and you know it's the case, so you can try to see how your diagnostics change when you. Sorry. You can have different assumptions on that collection of regions. You can change the distribution of parameters and see what effects it has on the diagnostics. And it's something you can do even yourself with if you have a grid of cloudy models or modern PDR models, if you use PDRs, it's something you can do actually. You can just simulate a collection of clouds if you want. You can then integrate all the line fluxes, put that in a single spectrum, and try to see how the diagnostics change if you do a collection versus not a collection. These are things that you can do to try to understand a bit what are the potential biases and if an average is actually physically meaningful. And if you can use an average to study some trends, maybe the absolute values are not going to be right. Maybe the general trends will be okay. It's going to go in the right direction because the average is maybe not right, but it's not too far from the truth. And there will be a dispersion if you use trends. And so you're going to get the right answer more or less. But I don't think there is an easy answer to that question.
So is it okay if we'll try to inject some kind of random or let's say normal distribution into the galaxies and perturb them in small scales and then try to
Yeah, you can try
recover
that, but remember that it has to be physically motivated. So if you start doing such things, then you have to ingest something that is that makes sense. And so in these situations, I would turn to simulations to use their own results and their own PDFs for the density I showed yesterday. Typically, is the first one that you can start with because it's pretty well known. So observationally, we have a sense of it. In the simulations, it's known very well, and I would start with that. And then there are other studies of spatially resolved galaxies that can help you figure out how all the regions you're talking about are mixed and to find some general laws that you can then ingest in your galaxy model, in your object. But I think you have to try. You have to try and see how your results change with the different configurations. And probably you don't know what is the right configuration, right? So it's kind of like an uncertainty on the model. You have to think of it as an uncertainty on the model, like you have uncertainties in the observations.
Thanks.
So Parit, you had a question on Slack. You want to ask it?
Do not hesitate.
Hi. So my question is, so in model development, so my question is mostly focused on nearby regions. So in model development, do you have often the focus to output maps or that are comparable to observations, for example, column density maps or cloud structure, or maybe H2 regions created by like a complex distribution of OB stars? And if not, why do you think we need this kind of focus? You already mentioned that your focus is more on the physics, but how does it help the common cause, so to say?
I'm sure I understood the question.
Can
you reformulate?
Okay. So in nearby regions, like Amrita said, we have a lot of complexity, and but we don't have enough observation, enough output from models that is directly comparable to observations. So, for example, we don't have column density maps or cloud structure or H2 regions that are created by more than one OB star. So do you think there's enough effort to bridge this gap, or since you already mentioned that the main focus is the physics, not the pretty pictures? So how, and do you think we need more focus there to have this comparison
I'm not sure how to answer that.
To me, it's a question to ask an observer. Is he happy with the models that the theorists produce or not? And the observers should ask the theorists what they want exactly.
And the happiness is a p-value in the end.
So I will go in the same direction that so if let's take for instance one key thing that we are trying to do as observers in nearby galaxies. We are trying to get the mass of dust and gas. Okay, so we all understand that there are plenty of variations, but on the other hand, we need to get this to understand better star formation and stuff like that. So again, what can we get from models in the Milky Way? Can we get, for instance, the uncertainty we can get from it? Can we get some kind of laws, for instance, as a function of metallicity that help us to do the jobs in nearby galaxies?
Well, it's complicated because you all have peculiar objects. You all have closer. You all have peculiar objects, so it's impossible to give you a universal recipe. But I guess it's the same for the gas. But for the dust, we have tabulated values of kappa. We have different wavelengths, or our models. You can directly put them in the filters of the most common observatories. But we cannot really do more than that. Huh? Yes, there are also plenty of tables giving you temperature, mass, etc. as a function of AV for a spherical cloud or for a cylindrical cloud, but more than that.
Yes, so to more or less answer that and also answer Pierre's question about where we have potential Milky Way models that fail with current research. Disclaimer, this is my PhD project and it's all trying to see whether the things that I found are indeed physical or whether there are numerical mistakes still in my code. Yes, so more or less what I've been finding in my research is if I were to compare dust masses that have been constrained by observations and what have been constrained using 1D chemical evolution models for nearby galaxies, and also single galaxy simulations that have been calibrated for the Milky Way, we always find that the dust masses that are calculated theoretical are much higher for the external galaxies. So now it is more or less the problem for my PhD for the coming 2 years is to try and solve it, or to try and find a way to find some traces in external galaxies to then solve this issue, which is then with me in collaboration with Jeremy Chastanet. Although the last time that I've been talking about it with him has been in March, and then there are more problems about that he has been tackling. So yeah, hopefully in the near future I can answer it. But yeah, that's something that I've been trying to figure out, is whether we can calibrate models based on the metallicity of the galaxy, depending on the phase of the ISM, where we can find the dust that are different from the Milky Way. So hopefully in 2 years I can give the answer.
We take rendezvous.
I feel like this is a very stupid question. So I'm going to frame it into a question, understanding, and maybe a follow-up question. The question is like, so in the past 2 days, we've been talking about turbulence, dust, PDR, galaxies. So could you put the entire thing in perspective for me as to where is the location of each of the said things, that is PDR, dust, and turbulence, or in a galaxy? Like, is it localized, or can we find it anywhere, or something? So for example, I would say, like, we know that agents are found in the center of galaxies. So similarly, do we have a location for the turbulence, dust, or PDRs in galaxies? Is the question.
Well, so this is a great question. In fact, I guess that turbulence, as Pierre has shown, to start with turbulence, it's everywhere and it is at all scales. Okay, so well, it will have it may have an impact in all the environment that you are going to look at. It can be at the scale of the entire galaxy in the diffuse gas. Okay, it can it will shape the structure of the gas. It also can trigger the thermal instability, so it can lead, in fact, to high density environments. And turbulence, I would say, I would include in turbulence dynamics, okay, because of the global dynamics of the gas. Even at small scale, you will have some kind of instabilities that you will see in any observable, in any maps. You will see some filaments, some stuff like that. So, well, the point on turbulence is that really it's everywhere. Then I will just answer about the PDRs. PDRs are also everywhere at all scales, because when you are looking at the diffuse gas, again, very large scale in a galaxy, the very nature of the thermal instability which shape your diffuse gas into several phases is due to the interaction of UV photons with the matter. Okay, and this interaction will lead to a lot of pressure at very large scale. Okay, and then of course, if you are zooming in on a planetary nebula, what you will see is a H2 region plus a PDR just next to it. Okay, so yeah, that's my first element on answer.
I have nothing to add to that. Great question.
I can just add before maybe that as far as cloudy models are concerned, when we do grids, we tend to not mention by fear that it's dangerous the words shocks, turbulence, magnetic fields, and cosmic rays, because we know they are everywhere. We know they exist. We don't know what is the right prescription necessarily. So the best we can do is to try to use some general prescription based on the best knowledge we have, sometimes assuming the Milky Way ISM conditions for lack of better. But of course, we know they are everywhere. And if some people don't put them in their models, it's often because they are afraid to put it more than because they think it's not there.
Right. So if our sun was an O or B type star, would we have expected to see a PDR around it, like in our solar system and in an early time of our solar system when the planets were not entirely formed? Do you think that would have been like a possible location of a PDR system? I don't know, like, because right now our sun is a G star and all the planets are completely formed in some sense.
Well, yeah, if our star was an O star, then at some point around, what is a PDR? A PDR energy, as the UV energy, where the matter reprocesses the UV energy and re-emits this UV energy that it absorbs in outer wavelengths. So if our star was an O star, at some point, somewhere in space, I don't know if it will be, well, it depends on the density of the matter around, but at some point in space, you will have a PDR, okay? This is what a PDR is. It's just the place where the photons are absorbed and it changes the state of the matter. And then, so yes, there will be.
Okay, this is a very silly question. Okay, we talked about like the differences between, I don't know, the Milky Way and the other galaxies. But like, what about, okay, the ISM in a galaxy? Like, do we expect differences? I don't know, if we look at the ISM in the core or in the peripheral regions of the galaxy, like, what do we expect, like, inside of galaxy?
You have variations, and it's very well observed. You know, you have variations with latitude, with galactocentric distance. And well, for the gas, I'm not an expert, but at least for dust, if you look at a few millimeter, you see that you have different temperatures. You see that you have different spectral indices. So yes, there are differences, and they are well documented. Also for the metallicity inside the Milky Way, we see variations depending on the location.
There are some works by Liszt or Isabelle Grenier that look at different regions within the Milky Way to look, for instance, for CO dark gas that will change with the environment. So they care about the local metallicity in these places. So I know just about the metallicity, but for sure it's very different. But yeah, I don't know if there is a review paper on that actually that would say how the Milky Way ISM is diverse. That would be a good paper to. If you know one, I'm interested also.
Thank you.
Okay, so maybe we can go to the next topic. There is no more comments. So we are going to talk a bit more. So we have already started talking about model complexity, but for the sake of it, so yeah, so the next set of questions. So it's first about something that I think several of you have discussed, Natalie and Vianney, I think, about comparing models, because models have their own cognitive biases. And so when you compare models, what do you do actually? Is it a way to validate your model, to say that it's two models agree, so it's correct, or just a way to estimate the natural uncertainty that we have, you know, the variance between models tell you, yes. So do you have any idea about that?
Well, the way I use model comparison is as a way to evaluate the lack of knowledge or how little we know about what the object we're trying to model is, how we should represent it. So if I think of it as an uncertainty, really. But then there is a whole process to compare models and to decide which model is best. And I started to discuss that yesterday, but I don't have time. But it's not because a model matches the observations very well that it's a true model. And because the way that the model is designed is biased. It's a choice, it's arbitrary, and it depends on the object you're trying to model. So it could well be that a single component model will match all your observations, and that doesn't mean the output quantities are right, even if all the tracers are well matched. And so so yeah, when you compare models, so in Bayesian statistics, you have the Bayesian evidence, you can use the Bayesian factor. And so you can calculate the marginal likelihood to do that. So it's the probability of the observations for a given model, which is basically the integration of the probability of the observations on all the parameter space. And it's difficult to do. It's difficult to calculate that. But if you do, then you can use that to decide whether one model is better than another one. Maybe you've done that already. So that's one way to decide whether one model is best than the other one. But there are different things you can do. So you can, I mean, or I should say there is an implicit assumption when you do the Bayesian factor like that, is that the a priori probability of the model is the same. So imagine you have two different models with different sets of parameters, or you have one model with one component and one model with two components, and you want to compare them. You can compare their marginal likelihoods, but that's only part of the factors in the Bayesian factor. In the bias factor. The bias factor also includes an a priori probability, which is very important, and it's often neglected actually, and it's too bad because that is the probability of the model regardless of the observations, independently on the observations. So that means the belief that you have that the model with the sets of parameters you include does represent the object you're trying to model. And of course, it's impossible to evaluate. It's completely arbitrary. You have to choose something. So the best you can do is to say, well, this model is very simple. It doesn't correspond to a full galaxy because the galaxy is more complicated than that. So the a priori probability of the model independently on the observation is just very low. You don't know how very low, but it's low. Inversely, a very complex model is going to be realistic. And another word for realistic is just to say that the a priori probability of the model is very high. And so when you do a bias factor, these two, the prior probability of the model factors in, and usually people will assume it's the same. So it's the same weight, it's the same probability, and you can just use the marginal likelihood. But in fact, it's more complicated than that. And I think it's interesting to reflect on that because it's really a way to think of the object you're trying to model really, and not just look at the metrics, how well the chi-square or the p-value or the marginal likelihood or whatever you're using. These are just, this is just a piece of information to tell you how well the model fits your data, but how well the model is adapted to the object you're trying to model, that's not in there. That's not in these metrics. It's in another metric that is unfortunately hard to compute. Anyway, so I kind of deviated here, maybe, but so the way that models are compared and the way that you decide within a set of models, it's complicated. There's a lot of literature on the topic, but for me, I use that as a way to evaluate my lack of knowledge on the potential representations of the galaxy. And since I don't have any prior knowledge on that, then I can assume they all have the same weight, and I say, well, I cannot choose, so they are equally likely. And then you can do some kind of model averages also. In Bayesian statistics, you can do Bayesian averages. Or you can pre-select a set of models that you deem realistic, and then do a model averages of just these models. That's also another way to do that. But that's the way I do.
So that was to address the question about when you try to compare model to observations, but you can actually compare models themselves. You know, you can compare the output of different models without even dealing with observations. So for example, there were some PDR comparison studies, some dust comparison too.
So I think this is a very important exercise, benchmarking. Sometimes it's not rewarding, but it means you're going to talk with the people who do the other models, your competitors, and you're gonna try to find out a well-set problem which does not bias the results towards one of the models, which is interesting per se. And at the end, you will know better what is in this black box. So I think it's very important.
So when you say you will know better, what's in this black box, so what is it that you're going to know? You know how it behaves, or you know how uncertainty it is, or you know if it's right or wrong?
You will know all the dirty tricks that everybody does to have your code compute actually something. You will know all the little details which you thought were not important, and in fact seem to give you discrepancies in some other situations. So I think it's a very good exercise, and also a sanity check that will improve your confidence in the results you get out from these models.
So it's a sensitivity analysis test in a sense.
Well, for me, I completely agree. For me, this is a fundamental thing. Any modelers will, when you implement a new process in the model, you will compare it with other models, just also to test that your way of seeing the physics is correct. You have a certain way, you are biased in your way of seeing a physical problem. You are trying to solve it yourself with your own methods, and others have developed other methods. And sometimes you don't know, or you have a wrong view of the physics, and this is a way to correct yourself on the way you thought of a physical problem. And it's very fundamental because the goal, in fact, is not to validate your model, but to invalidate the others.
That's the way to see.
was a joke.
Okay, so are there any questions, reactions to that in the room? Okay. So let's see. So I think the next question, we partially addressed it. It's something that you have discussed, all of you. So it's are the epistemic opacity of ISM models, so it's their black boxiness. And there are sometimes unjustified sophistication, an obstacle to what we do. And so the question that should we adapt the degree of complexity of our models to the quantity we want to derive? So you say definitely no. So it's better to have, and Natalie the same, better to have a complex model with a lot of physics, even if we fit only one line. And I agree too. So,
I disagree.
Okay.
No, for me, I disagree. I'm for a multi-approach. For approaching a physical problem with different views, simple views, where you can do a very fast parametric study, or complicated views where it's harder, in fact, to explore all the domain of parameters. You will learn a lot. Look at simulation. People have built numerical simulation, and what they are trying to do is to put more and more complexity to go to the higher possible resolution. You go to 2020 cube. 20 Shepakwa, I say, it's an English expression. But the point is that try to do your simulation and make a grid of parameter of your simulation with 64 cube simulation. You will learn much more out of this. If you do that for 2 months, you will learn much more on how your simulation is working than with very complicated simulations. So I'm for an approach that do all of these things together.
But we should also think about computer resources and time.
Yeah, but no. And I will also, I think the unjustified is unjustified. Yeah.
It's provocative. But so the question is that if you have both, if you have the simple model and the complex one, at some point you need to decide which one you prefer, which one you trust best.
Well, so I get back to the problem of numerical simulation. For me, I will learn much more about a most simplistic simulation, and this will make me trust my understanding of the physical processes. Then, if I have a very complicated simulation, and if I don't understand out of my knowledge that I build with this simple simulation, if I don't understand what is happening in this complicated simulation, then it won't make me trust this result particularly. This is...
So in a sense, you say that you need to have low epistemic opacity in your model.
I'm saying we need everything. We need to build our understanding on, I don't know, simple cases. Sorry. I'm just saying that we need all of this. We need multi-approach of the problem. We need to build our understanding on simple cases, and it's very important, and we need to keep doing that again and again and again and again, and then have more complex models, and to see the difference, or to try to understand why there is difference with this simple approach.
Comments, question?
I think I agree with Benjamin, because we really need toy models to understand what's going on physically, because with complex models, I mean, it's complicated to trust complex models, but it's easier to understand what's going on in toy models. And if the complexity is the model is too complex, how could we trust it? I mean,
But it depends what you mean by complexity. If it's, for instance, putting some sources, I'm looking for my kind of models. I mean, I'm not a modeler, I'm using models of models, like I said. But if there are some energetic sources that I can put in there and it makes a complex model, but these sources are not very important for all the diagnostics that I'm using, then yeah, sure, it's too complex and I don't need to do that. But if you know these sources exist, if you know they have an influence on your diagnostics, and if you know the ISM is complicated and it has an influence on your diagnostics, because you're using low density lines with critical density in my case, then if I use a very simple model, might have strong biases, and it's not going to help me understanding what's going on necessarily. So it depends on what we mean by complexity, really. If it's a justified complexity because it has an effect on all the diagnostics all the tracers that you're using, then I think you have to consider it at some point.
And sometimes you say really wrong things when you're trying to simplify things. I mean, I have several examples in mind where people say, okay, this should be proportional to that and this to that because it's this and that. Oh, so here I find this and the observation, so that's wrong. And all the colleagues were wrong. And then you take your complicated model and say, okay, this is not strictly proportional, this is not strictly proportional. So if you take that and that, you find exactly what was in the observations. So being oversimplistic is not always, I mean, toy models are nice, but you should be very careful.
But sometimes you cannot go further because
sometimes, but when you can, if you know the
yes.
physics, don't ignore the physics.
But to really grasp the observables, I mean, you could always put complexity in your models, and at the end, I think you will be lost in all the parameters that you have.
Well-built model give understandable quantities related to observations. I mean, good models which are developed by teams which are serious with that, they always give you the quantities that you need for your observations. I mean, if you take the PDR code from Madon, for instance, you have exactly what you need. It's if you take, of course, there are plenty models where you get plenty of things that are completely unexploitable, but well-settled model usually.
I think Jack is working on polarization. So we don't even know what we are observing in this case. So.
For me, it's a question of trusting things. When you're doing your observations, okay, you're trusting that the observation has been done correctly, that the instrument has been built correctly, and so on, and there is no too much bias. So I think this is the same in models, and I think that's why you're distributing your models, because you believe you're trying to do the best, and documenting them, you're trying to do the best you can. And I think you've been too negative on the first part of the tables, saying that you cannot, there is too many uncertainty and so on. I think, in fact, you're all trying to do things the best you can to put most physics into it, believing that the physics is right, even in outer galaxy. Then there is a question of using the model with the right input parameter, metallicity or whatever. But you would not distribute something that you believe that the physics is completely wrong. Well, I guess so.
I would say it's not necessarily negative, but critical. And you have to have a humble opinion of the results, knowing all the potential biases. But it's not necessarily a negative thing. I think of it as a positive thing, in fact, because then these biases, you're going to try to solve them in the future, and you're going to try to improve it slowly. But it's just a realization that things are complicated, be humble about the interpretation, stuff like that.
Well, I agree with that. So what you're saying is that the uncertainty on the quantity we have should not be underestimated. On the other hand, to first order, I don't believe that well, may be wrong, but I don't believe that the mass of galaxy we are deriving are wrong by an order of 100 or 1000. Okay. So even though there are metallicity effect and so and stuff like that. Okay. So it's we have to work collectively to try to decrease the uncertainty and to make a good estimate of the error bars. And I don't say that this is obvious, but you did it on your talk. You said that depending on the grains you have a factor 3 in the mass, but it's not a factor 100 or okay. So we're really all trying to decrease the errors by adding physics and so on the model. And I think we are going in the right direction.
The model first and then complicated ones.
Makes sense. Okay, comments, questions? Go to the next part. So now we are going to talk a bit more about the way people work. So it's here, the geeky stuff. Oh yes, the geeky stuff. So about the way we work and you think we are going to work in the future. So I think all of you develop your own codes by yourself or with in a small group, and you, in a sense, you have a hand on all the aspects of your code. And with the fact that we are going to have an increase in complexity, do you think that this will be the way in the future, or that at some point we are going to have to work a piece of a code and prospect about what the next generation is, how the next generation is going to have to work?
Well,
the next generation is here and they know how they work.
I should know better.
So I'm sure I'm not the one to answer this.
Well, I don't know, but in the models that we are developing, it's already working like that. There is a handful of people who have a complete knowledge of a single code, and then there are generation of students who are working already on implementing some part, some, I don't know, sub-function in a models. So it's working a little bit like that. I think that what is changing maybe is that now there is a question of should we have engineers working in the development of models, people who are much more, I don't know, efficient than us in developing models, so that they are building a Rolls-Royce of, numerically, because what we are basically doing is, how can I say that? It's artisanal work. Maybe it will be the development, like engineers will develop our the code. Yeah.
I already asked an engineer to help me for the second version of our test model because I was not able. Otherwise, it would have taken a century for the calculations. But otherwise, I like being in control, so I do everything. Voilà.
I think there is one tendency which is also more collaborative works. I mean, when I see you guys are all using GitHub, and it's already, you're using a lot of tools which are easy to spread. So, I mean, you know better than me.
So how do you work on your codes? Yeah, like that's the question.
Thanks. We have exactly the same conversation with MHD codes. I mean, we develop codes that are bad. They're badly written and they are inefficient, but they do the job. So when we have asked engineers to write the code, then we cannot work with the code because we don't follow the protocols. And then as soon as the code goes into the community and someone wants to use it for a particular program, they will mess it up. So basically you need the group to have someone with this training, but who wants to do astrophysics, doesn't really just care about the code. And the overlap of this expertise is extremely rare because we don't pay them as much. So a very highly trained computer engineer will find better opportunities than a postdoc in astronomy. So I think that is an aspect that we might want to consider, like in grant proposals or evaluations, having some funds for people who are dedicated to the project but have an engineering background and can support the team, giving them the desired flexibility and modularity in their code while maintaining the problem-specific limitations.
So I think an interesting thing in code development in general over longer generations is that the people that wrote a specific code that does something, they wrote it in their own way, especially if it's a new piece of code. And the problem is connecting, transferring that knowledge. And so something that we've done for code, for example, is having a test pipeline that every time you make code development, you check that your tests run the same way. However, doing that properly is very hard because if for example, for our test pipeline, it's actually really time consuming to do this. So for example, someone else in our group has essentially, every time you do a push on Git, your test pipeline just runs by itself and sends you an email if it doesn't run. And I don't know, for modeling approaches, I don't know do you have test pipelines? Is this something that would be useful? Yeah, that's my question.
I know that it exists for some codes, not for my codes. I don't have the test pipeline stuff plugged in, but for instance, the Meudon PDR code, I think that they developed at some point a test pipeline. I don't know where they are on that point, but they thought about this. And for other codes, astrochemical codes, I know that it exists. I don't know what mappings and Cloudy are doing, for instance. Maybe we can ask Brent.
The only code which has a test pipeline is Mesa, on which I took a bit of part, and this was because it's an engineer from Xerox who wrote it, and he's just using very neat programming rules, and so my English is so bad. Sorry.
I agree that this is the way our generation is doing stuff, but I think the next generations will go into the way of being more professional in making tests. Just because, as you said, with GitHub, we are getting more professional tools to spread codes, and this will come. You know, this is a bit like data. 20 or 30 years ago, you keep your data yourself. Now, there are rules when you're funded. You need to make your data public in some way, and you're spending times to ensuring that the data you're putting is correct. And I believe that this will come for codes. Okay, you will be in one way or another funded, and your funders will ask you to put your codes public with some way to be able to reproduce results. This is a tendency of research today.
So I want to say, based on this point, that maybe we don't need to wait until this happens organically. So maybe we can actually add coding practices as a course in our advanced, like in our graduate programs, because I don't see it very often in physics or astrophysics graduate programs. So it might be something that we must do.
So since we can't attract engineers, we have to become ourselves.
Yes, that is, for example, something that is being created at Leiden University in the Netherlands, where for your master's degree, there are several specializations in the physics of ISM, in cosmology, but there's now also a special program where you get a lot of computer science courses to specifically focus on the data science aspect of astronomy and more or less become data engineers so that you are more well versed in the programming part rather than the scientific part and more or less have that bridge.
I'd like to add something if I can. It's a little bit off topic, but it's related because here we're talking about developing models. So I don't develop models, I use models. But I think it's also interesting to think of the way that we work in when we use models. And the models are developing in complexity because the data is also developing in complexity with things like SK, for instance. And the ELT after. And so the data is always becoming more complex. It takes more and more storage. And the models kind of scale up to that also. And the models can be very long to run. They can require a lot of memory, etc. So you need to have calculating clusters, and for simulations, it's even worse. And so it always makes me think that we are not all equal in front with the computing power. And so I'm afraid sometimes that some people, students, are going to be limited in their way that they can use the models because the models are too demanding in terms of computing power. For instance, now things like Bayesian statistics, yeah, it's great. But quickly, if you do MCMC codes, the laptop is not going to be enough. And so what do? Then you have to have access to a calculating server. So I think it's important to have global policies that give access to servers for calculation for students wherever in the world, because otherwise it will create huge inequalities in the access to the data, but also in the access to the computing power to use the models. And I'm a little bit afraid that these differences are going to increase in the future because we like to do more and more complicated things, because we want to find more interesting things and we want to go into more details, always more details. But at some point it explodes, and then you need to have the right hardware, the right tools to do that. And so not everybody has these tools. So something that even 10 years ago, we didn't have to worry too much about, but or maybe for simulations they did, I don't know. But what I'm saying is that right now, even a very simple model can be so demanding that you cannot even do it on your laptop, which is crazy.
Just to comment on that, I think another solution is to have pre-computed grid of models, and there are many people who provide, in fact, their simulation and their models to the community. Yeah, I'm taking, for example, the Galactica portal, which is very smartly done, where anybody in the world, whatever simulations are running, whatever code is behind, can provide, in fact, to the community the result of the simulation. And the same applies for modeling. The Meudon PDR team, they have built also this very nice interface where you can download tens of thousands of different models, so you don't have to run them yourself. You have all the results. You can simply analyze the results of the model. And well, this is one way to reduce these inequalities we're talking about.
I would like to moderate a bit what you're saying, because what I see is that supercomputers today are evolving from being used mostly by simulations to analyze data, in particular because of artificial intelligence. And this is something that all the governments over the world are pushing. So what I want to say is that we should not think ourselves are unequal. The thing is, our future is in our hands. Access to computer is expensive anyway. So in order to access supercomputers, you have to compete as in order to access observations. And so in order to compete, we need to get as professional as simulators, okay? Ramses has this suite, and they show that they can do what they will announce. And so in modeling, we need to do the same things, okay? So this goes in the same direction as working collectively to have benchmarks between codes, to benchmark your codes on the same case all the time you're doing. And we have to do this, else we will not have access, but it's not because they don't want to give us access, it's because we are not professional enough.
Comments, question? Okay. So what's the next question? So we are a bit late, so we are going to skip some. Wait. So I'm going to share the screen again to show you. So maybe this one is a bit too technical. Oops. Wait. Technological feedback. So I don't see my full screen. So yeah, thank you. So I think we can skip this question because it's a bit too technical, but let's talk a bit about machine learning, because I know that several of you in the room are interested into that. So do you have any ideas about how machine learning will impact your model development? So we know that machine learning can help you really analyze observation, compare models and observations, but really, will it help you also really compute your model?
Well, I just know that again, the Meudon PDR teams have thought about that to try to speed up, in fact, the computation of their models on some part of the physics that takes a long time to run. Okay, so you take any part of the physics. Let's say that you want to solve the excitation of H2. I'm saying a stupid example, huh? Whatever. And let's say that this part takes a lot of time. Then they thought about the idea of implementing machine learning in order to solve this part, this specific part of the physics, speed up their algorithm. This can be so I don't know where they are on that subject, but I know that they want to do that. And this can be applied to basically anything. And when you increase the complexity of the model, the complexity of the network of species, you know, with thousands, tens of thousands of species that you want to solve, tens of thousands of levels that you want to solve, maybe some of the people or some of the developers will try to implement this kind of technique to basically speed up the calculation. I don't think it will replace. It will be something that we have to switch on and off, because well, I'm not an expert of machine learning, and I don't know. Well, if I had to do that, I will be very shaky on trusting, because I don't know anything about the subject. So maybe we can
hire an engineer to do that.
But I have a question about that. Actually, when you do that, there's an uncertainty due to the prediction of the machine learning kernel. So how do you propagate the uncertainty then in the rest of the model?
Yes. So I have an answer to that. I'm really not an expert. I'm just saying what I know about the Meudon PDR team. I know that they did that. They want to do it. And then I don't know what they are in the exploration. I guess, yes, there is a lot of errors, but I have no idea how to answer your question. This is my answer.
So just as a follow-up, in fact, in the ANR DAOisms, we are working with Meudon PDR. And so we have a paper that is almost ready where we are using the grids. The difficulty of grids of codes is that they are regularly sampled, okay? And there is no reasons why our quantity are continuous. And so on this paper, what they do is what we do, what students do, is using neural networks to interpolate the grid, and they show that neural networks solutions are much better than any other interpolation methods, much faster, much lighter, and with control errors on models that have not even been seen on the grid. Okay, so this is one of the future of the stuff, because for Bayesian approach, grid is not very good, but this model, this kind of neural networks will allow you to use those models in Bayesian approach.
Yeah. This, I completely agree with what you are saying. In fact, once you have a grid of models, this is the best way the best way we know of interpolating this grid on a subgrid models is with these techniques. But I thought that the question was directed in the sense of model development, the physics of the model itself. But yeah.
I mean, no, so it's doable, and one advantage that machine learning to mimic the result of the output of a model becomes even more efficient when you have a high dimensionality, so high number of parameters, than any type of interpolation you can do. And it's almost instantaneous. It's just matrix.
So I'm not a modeler, but I'm writing code for something else, and I'm interested into because I'm doing software for data reduction. And my director is asking me whether this task will be done by ChatGPT tomorrow. And so at start, I thought not, but I'm changing my mind. Because if there is GitHub with the help of Microsoft and his power, because GitHub has been bought by Microsoft, are training a neural network to help you to write codes. This is called autopilot, no, copilot, I think, copilot. And in fact, you're starting to write your commands, and he will search in his database what kind of codes he can write for you, based on the GitHubs, all the code that has been posted on GitHubs. And for instance, advection, you're typing, I want to advect the flow. And this is the example I've seen, okay? And it writes you a Python stuff that will do it. It does not need that. You don't need to understand it, okay? It can be wrong in details, but at least the main stuff will be there. And I'm pretty convinced that this will increase the throughput of developers. So we still need to understand what we are doing. We need to oversee what the stuff the intelligence artificial will do, but the throughput can be much better.
That's a bit dangerous for the students. I mean, all the students that come to our team, whatever their level, I wrote a little practical work set of questions. And one guy answered to all the questions in one day. Normally, it's at least 2 weeks. And then I asked the questions to ChatGPT, and this guy just copied everything. And in the end, he didn't understand everything. No, but I mean, you have to understand. You have to understand. So you should never start asking ChatGPT for anything. It's first ask yourself, no, but that was really bad because this guy was not stupid. But so it's too long. I want to work on my training period, but I don't like, I mean, I think it's dangerous. I mean, it's for students, it's really, you can take shortcuts which are not good.
As any technology, you need to learn how to use it, but we should not be against using technologies that will help us in the future. I think we agree. I think we agree.
I'm not against. It's not what I'm saying. I mean, sometimes you write a code, it's shit, you put it in ChatGPT, you say write it better, it writes it better, that's fine. No, but asking the physical question to ChatGPT or the chemistry question,
You have an answer.
you have an answer. Yes, you have an answer.
I have a personal opinion on the use of software that is not open source and not free. It shouldn't be part of our work. We should use as much as possible open source software, free software. And if you have to use a software that you don't know how it's working, it's not free, your university might pay for it. It doesn't mean it's free. Is it really the way that we want to use tools? Personally, I don't think so. I don't think it's good to have all my data taken by somebody just because I'm saying, yeah, I'm putting my piece of code and all my information is going to be used for something else for sure. And it appears to be free, but it's not free. So maybe there's a general debate to have. It's not the place right here, but I'm just taking the advantage to say it right now. The opportunity to say it is that we should also reflect on how we use these kind of tools and whether they are ethical or not. And ChatGPT is not ethical, for instance, but there are others that are, and they are doing pretty much the same job as ChatGPT. So for this, why not? But it's important to choose the right tools.
Just to react to what you say about the efficiency of the ChatGPT to produce code. Actually, maybe it's very efficient and very speed. The code is good to do what we want today, but I think from the long-term point of view, I think it's very self-destructive approach to do that for 2 points. The first one, human capability to remember things, I think is very versatile. And in a very few decades, we can forget everything we know. And for instance, in my laboratory, we have some contact with nuclear scientists, and they explained that today they were struggling to do some compute formula. And they did discover in a very old paper in the 80s, we was capable of do the same calculation and we didn't know. So there is a real issue. And about ChatGPT, if today we say, okay, you do a very clean code, I will use it. In 5, maybe even quicker, we do not know how to program. And you talk about the fact that the code is in open source. So the first issue is, I think in a few years, we will not able to proper code ourselves. And the second issue is the fact that ChatGPT will be not in training again on a new code, because humans do not give to him a new proper code, because we were not able to provide the database, the training database, because we will not be able to code. But maybe there is a thing that EA can produce their own database with generative approaches. But this is a third issue, because we will not able to have the step back and the competence to have critical see of this in posteriori. I don't know if it's clear, but I think it's very useful. If you look at the code of ChatGPT, okay, I didn't thought about this kind of method to code. I will try to understand and improve myself, but I don't think it's a good way to say, oh, I put in my black box and because the result is nice, and in the long term it will be destructive for engineer and analysis as well, because we not.
I mean, right now, ChatGPT is not inventing anything. It's natural language processing, so it's just predicting. You know, when you start a text, when you start a code, is probabilistically, what's going to happen next. But you can expect that ChatGPT's cub, so the next generations might be much better at really extrapolating the way we code now and really invent other ways of coding. That's
just when I mentioned open source, I should have said that it's in the perspective of open science. I mean, there are ethical issues, but there is also the perspective of open science and reproducible science. It's very useful to use open source software for that, because then you can always get that piece of code, run it again, and for future generations, it's important, I think.
So ChatGPT is an efficient way of knowing what other human beings have been coding, but it's not a good way to invent new codes, I would say.
So just as a survey, so who is using machine learning in their projects right now? Can you? Yeah, okay, 1, 2, okay. So it's not even half. Okay, so 1/3. It's already, a lot, yes. 10 years ago, no one would have answered. Yeah.
And who is using ChatGPT?
And who's using ChatGPT in their project? Okay, so about the same, yeah. Okay, so any more questions, comments on that aspect?
No, I just wanted to counterbalance a little bit the bleakness of the approach to ChatGPT and just say that people who cannot code now are the same people who will not be able to code, like the same kind of people will not be able to code in 20 years. So now they go to Stack Exchange, we go to Stack Exchange, and then they will go to ChatGPT. The people who are creative, who invent new things, will create new things. There are minds that work this way, they like to solve problems, and they go there and they invent new stuff. Hopefully they share it with the rest of the world, and then ChatGPT knows about it, and then this code solves my problem too. But it's just a different way to search for information. Right now, it's a different way to search for information and to extrapolate on what the collective of humanity has done so far. If they reach the point that they are more creative than us, then okay, then they take over and then we just relax.
So when you ask...
But creativity is always our thing.
So ChatGPT is giving us answers based on everything that has been published on the web, while on Stack Exchange, when you ask a question, you get an answer for someone because it's not on the web, it's in his brain, and he's going to enter it, he's going to add data to...
But that still exists. I mean...
Google.
Not accessible, yeah. Okay, so maybe we can take a last questions because we have only 10 minutes. So let's do an easy one, just to finish. Yeah, so for example, this one. So, so how do you see your field in the next 20 years? I mean, 20 years from now. So yes, what do you think are the open questions that are open now that will have been answered in each one of your favorite topics? Easy.
I don't know if it will have been answered, if we will have an answer in 20 years, but I think that we will know much more on the way turbulence is dissipated and transferred from one phase to another. For instance, this is where I really believe we are going to make progresses on that subject. For two reasons. The first reason is that I know that Pierre and others have new ways to analyze maps and structures that exist in the turbulent field. This is one point. And also we will have a lot of observational data, in fact, with SKA and so on, that will describe much, or give us a lot of information, in fact, about the multi-phase and turbulent nature of the ISM.
I see that there is something about future instruments. So for me, I'm excited because it's in 20 years. Yeah, that's about right. So I mentioned Habitable Worlds Observatory. And so it's going to be a future NASA flagship that is the real successor of Hubble, because it's going to be an observatory, multi-wavelength, huge. I think it's 8 meters at least for the outer diameter. It's a segmented telescope. It's becoming concrete. And why is it nice? It's because I guess you can argue that it's going to go to the far UV, and far UV spectroscopy is maybe the domain of choice for multi-phase ISM. I know that not anybody is going to agree, but you can do a lot of things ISM related with far UV spectroscopy. And right now, the only thing that exists is HST with COS. COS is losing a lot of sensitivity every year. There was Fuse before, it's gone. So there's really just HST right now. And so it's very good that we have a future with the far UV spectroscopy, especially with such a beautiful telescope that we're going to have. We're going to be able to do a lot. And it's going to be so sensitive that you can do a tomography of the ISM in nearby galaxies, and you can tackle a lot of the things we've tackled right now, like molecule formation in turbulent layers and plenty of things like that, with the help of absorption lines in the far UV, cooling layers and mixing layers and plenty of things. I mean, all the ISM chemistry, and there's really a lot. So I'm excited about that in the next 20, 25 years at least. You know.
Well, there will be, for the next 10 years, you will have the JWST, I think, which will solve the nature of the nanometric hydrocarbons. And then I hope we will have solved the question of the composition of the big grains. Especially, I hope that at that time we will know what is the temperature of the polarized SED, because it's something we don't know. We know just the temperature of the total SED. And if we knew the temperatures of both, the question would be answered in a question of days. So it will be a matter of days. You know, it's very easy to check things.
I have no idea. I'm a theorist.
Yeah, but even if you have, much more powerful computers, is there a quantitative jump that's going to allow you to really do something that you can't do right now, but that will help you what you're trying to do?
I think it always will come from the observations in fact.
Yeah. Do you all agree with that?
And so what I expect from the future instruments is surprises and things we didn't think about. I see the new images by JWST. I had no idea we would see this kind of thing. I was completely taken by surprise. So, and honestly, I think it's still driven by observations. We are so far behind as theorists to explain what is seen that. So I hope we will understand more turbulence, and and on the multi-phase physics, because Benjamin is working on it. But I have no idea.
Any comments or questions in the room about that aspect? Do you all agree that all the progress comes from observations? Okay.
Now maybe from the generative models, maybe there can be some progress made. We can, the problem of weather forecast predictions, for instance, we have very sparse data collections both in time and space, and having better fluid dynamics models, even if they come from artificial intelligence or physically motivated things, will allow us to guess what the field is in between. And so maybe deep projection models because the same problem exists in astrophysics. We only have a projection of our sky, and hopefully we will be able to deproject better. We're already starting with Gaia. It's a fantastic, the dust maps we can produce now.
So the answer in 20 years will be the 3D structure of the ISM. That's what you mean?
Yeah.
Yeah.
For astrophysics, I would say we will get better physics. Now we have the data. Gaia data is very precise, and now we have Gaussian models to fit the structure of the dust. if we have better physically motivated models for this dust structure, then we can better constrain the actual structure of the dust. But it will be disproved by observation, so.
No worry.
Okay. So thank you for you and to everyone here. So